have been, apparently while I was away, I have been volunteered for a second talk, which I am happy to give. And apparently people would like to know a little bit more about what is the business with all these type universes. Okay? So I'm going to, there are several ways in which you can motivate type universes, some of which are very serious sounding, but I'm going to go the pragmatic way to explain where this comes from. Keep in mind, it's not the only motivation for having type universes. There could be others. So let's begin with an observation that in type theory, which is essentially a formal system, one way to understand type theory is that it's a formal system, there are judgments. Now I have to decide what continent I'm from. Okay. Sorry. He's not watching. It's okay. The English people are not watching my spelling. There are judgments. There are essentially two kinds of judgments that we want to have. One is equalities, when you say that A equals B. But this is not what we're concerned with. So these are things like if you take the first projection of the pair UV, that's equal to U, right? So things like that, we're not interested in that right now. The other kind of judgments that you see are judgments that say essentially that something has a type. Okay? A has type T. There are several ways again to understand this. One way to understand this is, if you're not familiar with type theory, is to just think that types are sets. And in that case, this says A is an element of T. But there's another way, which is also quite important, which says something that means, which is much closer to A is well formed. And then we might put in parentheses, according to rules of construction for T. So in this case, you think of types as recipes or ways of constructing things, making constructions, and each type has some rules on how you make constructions for that type. And so then you think of this as, this is witnessing the fact that A has been well formed or constructed the right way according to T. And you don't think so much about sets anymore. So, for instance, something like this. So you would, presumably your syntax would allow you to write this. Okay? And if you just write this, it's just like two things. But as soon as you write this, and then, by the way, people often put this here, because there was a German who said that we should write this thing here. So
he wanted a much longer one. He had a much longer one.
Yeah, but he also had kind of two-dimensional syntax and things that, yeah, it was, okay, let's not go there. So you would expect this, and the way you would read this is well-formed, okay? It's not just saying it's well-formed, it's telling you it's well-formed and also what it is. It's a well-formed thing of type, this funny letter, which then we understand as natural number. So another example would be, if you try something like, you have like 7 plus 3 and the variable x. Is this well formed? Now it's going to depend. So first of all, you just cannot have a free-flying variable, so you probably want to also assume that this variable has a type. It has, let's say, if it has a type A, then presumably we should be able to establish that this has a type n cross A, assuming that there is a type like that called Cartesian product, and somebody has to give you the rules. It's all about the rules. But the point I'm making is, think of this as saying something is well typed. That's option 1. Option 2, think of this as saying this is an element of that set. Both are possible, and we are going to discuss both. But I am motivated from this well-founded, well-formed business, because when you implement a proof assistant and when you use a proof assistant, what does a proof assistant do? A proof assistant checks things for you and tells you it's okay. How does it tell you that it is okay? By validating such judgments. So the main form of establishing a theorem or anything at all in a proof assistant is to say, this thing, colon, that type. That is essentially all that is going on. And when you implement a proof assistant, that's the thing you're going to implement. How do we establish such things? Following some rules. Okay, so let's take this seriously. Okay, so we've established that this is well formed, but is this well formed? There should, like everything I see, like whenever I have an opportunity to write down something stupid, the proof assistant should say, wait, let me check this thing is not stupid. So in principle, I could write some garbage here, and then the proof assistant has to worry about that. How is it going to make sure that this is well formed? Well, the most natural way would be using the same idea. So we should, to say that this is well formed, we should have the ability to say something. So let's just actually start with this one. Also, why is this well formed? Right? So you would say, N is well formed means N is well constructed according to the rules of what? And then this is where you write type. And you say there is a type of constructions for making types. There are rules on how we make types. Here's one rule. It's called Cartesian product. Here's another one. You could put an arrow like that, and now you have to be precise about what this means. And then there can be a third one, and a fourth one, and there could be inductive types and co-inductive types, and there could be lots of things. Yes?
Is type well formed?
Of course, I paid him to ask the question. So, right, this is the obvious next question is, so this is how we're going to say that this thing is well formed. We'll say it has been built according to the rules of type. Is this well formed? Very good question, Frank.
Sorry.
Yes.
I couldn't resist.
Yes. So, what is the answer? Well, Martin Löf gave an answer in 1971-ish, 0-ish. He said, oh yeah, type in type. Type is well formed because it's a type. When he was young. So, then somebody even younger came along and said, no. And he's used this fact to derive a paradox in type theory. It is a Burali-Fortit style paradox. Ordinals, define ordinals in type theory. The type of all ordinals is an ordinal, is bigger than itself, la la la. So, he said, no. This is the French no. Not French. Okay, so this does not work. Actually, it kind of works. You can do this. But then you cannot use type theory as a foundation of mathematics. You can still use it quite successfully as a programming language in which you allow infinite computations, non-terminating computations. There's no problem, you can do that, but not for foundations of mathematics. So we need a solution. Well, let's go back to set theory. Set theory kind of had the same problem at one point, which was, is there a set of all sets? And it was a problem. What was the solution? The solution was to say that apart from sets, we have even bigger sets called classes. Yes?
But actually it was types like Russell.
Ah, yes. See, I paid him too. Where did set theory get its idea that there should be sets and classes? Well, I don't personally know, but there is a precursor to that, which is Russell's type theory. So we're back to type theory now. Russell's theory of classes, right, said there are these levels of classes, and you're not supposed to just throw them all in the same basket and mix them up, because then you get set and class and so on. So we could have a hierarchy of these. And we would say, oh, okay, so if set theorists have sets and classes, how about if we have types and kinds? And if you read literature, say, on the ML programming language family, they will speak about kinds there, okay? Of course, right? The next question is, how would you know that this is well-formed?
Just assume.
Well, but even if you just assume that it is well-formed, here's the technical problem. When you implement your type theory, you will still have to deal with the fact that kind appears somewhere. Because I'm going to write down things like type, arrow, for all A, type, A cross, type, kind. Is this well-formed? What if I put kind here? Is it well-formed? So you will, you see, but you will have to answer the question because the user will write it down. Yes? They will write down, the user will write down everything that could possibly annoy you. Okay? So you will have to answer the question. It's doable. ML does it. No problem. You can, like the ML programming languages, stop here. But there is a considerable overhead. And it's not really that well motivated when you're thinking about formalizing mathematics, because when you're formalizing mathematics, this is going to be a bit of a bummer, because you will have to stop here. You can well imagine that you want to maybe prove some statements about classes of classes, so some sort of superclasses. Why would you stop? So the answer is, well, you don't have to. We can keep going. The advantage that you will get from that is that it is going to be technically simpler to implement. There are variations on how you implement type theories, and usually the ones where you can just keep going with this stuff are a little more convenient and also a little easier to explain to everybody, because I'm going to explain now that this just keeps going. And if I said, no, it has to stop like after 4 levels, everybody would get on my case and say like, why 4 levels, why not 5 levels? And then eventually I would just give up and say, I have as many levels as you want. So,
Let it be implementation defined and then...
yes, so I mean, of course you could say, maybe you let the user tell you how many levels there are. Everything is possible. But let's just run with, just so we can imagine something, let's run with one option that is often adopted, then also maybe slightly there is a variation. So of course that one would be that you start with some level, type 0, and now instead of saying type, kind, collection, super global, I'll just use numbers. So it's say type is well formed because type 1 is well formed because type 2 is well formed, and so just keep going like that. You just index them with natural numbers. So that is a possibility. But if you do that, you will now have to answer some other questions. In particular, whenever you have some type construction, you have to decide where are you going to put it. Because every type has to land somewhere in here. So for instance, I will ask you, why is this well formed? What do you want to write here? 0. Well, yeah, we might as well start with type 0. You see, it's not really necessary. We could start with type 17 if we wanted to. There is a lot of freedom here on what you do. So for instance, there's a recent paper where these are rational numbers. It's kind of fun.
Or actually reals as well.
That could be next year's paper. You can do that. Right?
No, it's in that paper.
It is already in the reals. Oh, okay.
Oh yeah, it's answered algebra.
So you can have lots and lots of these. Okay, so here's one that's slightly more interesting. Suppose you have a type at level m, and then you have another type at level n. Where do you think we should put this type?
The product. M times n.
M times n. So when m is 0, that's going to be very special. Yes. Because 0 times anything is 0.
We start the natural numbers at 1.
Okay, so you need something there. Okay, so what is your guidance here? One kind of guidance is that it's going to be really bad if you create a cycle. Because once you create a cycle of universes, the first one is the second one, the third one, and you come back, that's going to allow Girard to run his paradox. Okay? So you don't want that. It needs to be without cycles. Other than that, well, if we're sticking to this idea that we are saying that a thing is well formed because it's contained in some type something, well, they should every type, whenever you have a type, whenever you have one of these types, there should be one afterwards, right? They have to keep going if we're not going to stop. Yes, so one possible solution here is max mn. Just put it in the bigger one of the two.
Plus 12. Plus 12.
No. No. So where do you want n cross n to live?
That's the smallest you can go. No.
Where do you want this one to be? You want it to be in type 1?
No.
You're happy with type 0? Okay, so then we don't need type plus 1, yeah? Okay? But you are raising a very good point here. You need to think about what you want. Because, depending on how you set these things up, your universe, oh, by the way, these are called type universes. These things are called type universes. Depending on what you do here, your type universes are going to be or closed for certain constructions. So for instance, if I have this, and if I have this, then type 0 is closed under Cartesian product. Type 1 is also closed under Cartesian product. So every one of them is going to be closed under Cartesian products. And because the 0th one contains natural numbers, the 0 one will now contain all finite products of natural numbers. So what are some other ones? Let's just do one more. If I have something at type n, and then I can map into type n. So I go from m to n, like that. Where is the product going to be? So this is the product of types. The thing to keep in mind is, so for instance, I could have it like this. I could have B, I would think of this example. A is natural numbers, and then I have, I'm skipping over lots of these details, but imagine B of 0 is natural numbers. B of 1 is natural numbers cross natural numbers. B of 2 is, or even worse, something like this. So some types, they all live in type 0. Then we take their Cartesian products, where do we want to land? So if I now say here max, which is a reasonable thing to do, now type 0, and in fact every type, is going to be closed under pretty large products. So it cannot be a small thing. Somehow, intuitively, it has to contain a lot of stuff. And Mario is going to explain how do you think about this set theoretically. Because if you think of these as sets, you're now saying strange things like, you see, type 0 is going to be a set that contains the natural numbers, and then maybe it contains all Cartesian products, let's say also function spaces. So it's like a set that contains natural numbers, then it contains all exponents of natural numbers. In fact, it contains all products of all families of natural numbers indexed by things that are already in there. And you can throw in co-products as well. And it's set theorists study these things, but I'll stop here because Mario will tell you about them. Yes?
Can I ask you something?
Yes?
Could that n over there depend on x?
Which one?
Type n.
Yes, okay, so that is a good question. The way I set things up, I'm using 0, 1, 2 as external natural numbers. I could have just as well used sticks here. Okay.
Sure.
Yeah? And then I would hope you don't think that sticks are part of the syntax of type theory. But these are external numbers. So this is a schema, this is a schematic rule where this is supposed to be a specific numeral. So in that case, you can't stick here a variable. However, proof assistants allow you to do this kind of thing. Like for instance in Agda, or in actually also, I think Mario will show this. In Lean, you do write type alpha, where alpha is a variable.
Oh, that's what's called universe polymorphism, right?
That's fancier, and Mario is going to talk about it if we let him.
May I ask
Yes.
one question? I didn't want to preempt you again.
Yes,
But now that you're stopping,
Yes.
so Joseph said I should have talked about set theory. I forgot about that. Is it reasonable to say type 0 is V, the set theoretic universe?
Yes.
Okay, thank you.
No, I didn't. Yes, I understand your question. Mario will answer it.
I'll
You the other one.
use the second.
Okay, Mario, can you answer it before my question gets forgotten?
Yes, well, so I think I should
Exactly.
probably finish the talk
We
before.
planned this really well because the audience keeps asking the thing we're going about to say next.
Yeah. Right. So the goal here is now we have a bunch of type universes in type theory, and we want to understand sort of what they mean in intuitive understanding, where intuitive understanding means in the language of set theory, because I'm sure you all love set theory more than type theory. So, as Andrej said, we have representations of each of these types as, or we're able to construct a number of different types. And if we interpret each type as a set, then that gives us a way of understanding what this, it's already been erased, but if we have if we have some expression and it has a type, then we want to sort of interpret this as like an element of some set, which is associated to that type. So the basic idea is that we're going to take each type and then map it to sets in hopefully a natural way. For many of these, it's very obvious, like if we have the type natural numbers, then clearly we want to interpret this as the set of natural numbers. If we have the function type nat to nat, this is, sometimes you can write it like this, where you have the collection of functions from natural numbers to natural numbers, or the Bauer space. And if we have products, then those are going to be interpreted as the Cartesian product instead of C. So this all sort of works. But now, well, so what do we do with this, right? Like, we have this type, and, I claim that we're supposed to be able to map all of these things to sets in this way. And so we have to map this to a set. And this set has to contain the natural numbers. It has to contain the power set of it has to contain the functions from the natural numbers to the natural numbers. If we throw in here, like, natural numbers to bool, then this is basically like the power set of the natural numbers. So this type is going to contain the power set of the natural numbers. And in fact, it's going to contain the power set of every set that shows up in it. We end up with some sort of closure conditions. So I could say that, like, if we have this type, let's just call it U, then the natural numbers are going to be in it. We know that that it's going to contain I'll just say that it contains the power set. This is not quite the power set, but close enough. It's going to contain the power set of any set which is contained in it, right? It will contain Cartesian products. It will also contain these indexed Cartesian products. So the way that you would write something like that is that if you have a set, and you also have a family, you have B, I, where I ranges over A, that if all of these are in this set, then the product over A of the I, this also has to be in U. So the conjunction of these is this is a little bit different, but this is essentially the definition of Grothendieck universe. And so this is basically something that Grothendieck was studying when he was trying to set up the foundations of category theory, and he noticed that if you have sets that are closed under all of these operations, then they allow you to do a lot of things, and essentially this is sort of rediscovering that, like, okay, if we need these types to be sets, they'll need to have these strong closure conditions, okay? And so these are going to be really, really big sets. It turns out that in ZFC you can prove that these are equivalent to the V kappas, where so if you have such a U, you also have to impose a sort of technical condition, which is that it's a transitive. I won't explain what that is.
You can push this board all the way to the top and write on the next one.
Good idea. Yeah. So, if you have a Grothendieck universe, then it's equivalent to the kappa, where kappa is an inaccessible cardinal. So what's an inaccessible cardinal? I don't know whether I should explain that for the people here. But roughly speaking, it's a cardinal that obeys analogs of these conditions for ordinals. So it's got to be closed under power set, or the sizes of power sets, and it's got to be closed under unions of length up to the size of kappa itself. And within an inaccessible cardinal, within one of these VKs, you can actually construct a model of ZFC. So it's more powerful than ZFC. Because you can construct a model of ZFC, and this you know because of this from Gödel's incompleteness, that you can't prove the existence of any of these things in ZFC itself. And at this point you might be thinking, like, hold on a minute, like, are we really allowed to make these assumptions, right? Like, we've now said, okay, we assume the existence of these types, and now I'm telling you that actually you can't even prove that these things exist. These are so large that ZFC can't even prove the existence of these types, and I don't even just want one, I want a bunch. I want a whole family of them, right? And they've all got to be inside each other. And I guess the short answer is just deal with it. We're just going to assume the existence of these inaccessible cardinals and be happy with the fact that at least set theorists have looked at these large cardinal axioms and they seem all right. But yeah, it is in fact a stronger, it is a stronger assumption than just ZFC itself. And also, the fact that it's inaccessible also depends, I mean, from this construction, it does depend a lot on the operations. So if you didn't have this, for instance, then you wouldn't need an inaccessible cardinal. So if you didn't have these index pi's, you wouldn't get this clause, and because of that you wouldn't get inaccessible cardinals, you would get something weaker. So for instance, in HOL, you have something that kind of acts like these, where you have one universe of all of the types, and because the types are closed under the non-dependent product, so just with the arrow, but they don't have dependent types, you only need kappa here to be 2 omega, which I guess the omega, the 2 goes on the other side because ordinals are weird. For lean, it's going to suffice to have omega inaccessible cardinals. And this is a slight lie, slightly less than this in that you only need n inaccessible cardinals for every n, but you can't actually construct the full sequence of all omega of them in any particular proof. In Agda, because they also have the ability, so they have these products, but they also have inductive types. Lean also has inductive types, but they don't They can sort of be expressed in terms of these things, and one constructor which is also in a similar spirit. In Agda, there's this thing called induction recursion, and because of that, you can construct models of type theory inside a single universe, and so that gives you a even stronger closure condition, and because of that, you actually get mallow cardinals, which are sort of the inaccessibles inaccessible. I won't describe what the definition of this thing is, but it's an even bigger kind of large cardinal. Then there's two because of the way that the indexing works in Agda. Also, this is a slight lie because there's another property of the text that I'm not going to explain here, which actually makes this a different kind of theory, but for a sort of similar theory to this, with induction recursion, you end up with mallow cardinal. Okay, so what about cock? I actually am not entirely sure, but I think it's on a similar level to lean. So there's a bunch of additional things in cock that make it a little bit more difficult to analyze this, but I'm pretty sure that it's in the same ballpark.
Yeah, so you were saying that like we have a type theory, a formal system over there, and we are interpreting it inside of set theory, right? Okay.
Mm-hmm.
And then we need large cardinals, whatever.
Yeah.
But how do we get from here to the fact that you are about to show us that you can actually talk about the cardinals inside of the formal system?
Yeah.
Doesn't that raise the level that you need to interpret it?
Well, so in the system, we'll be able to say type 0, we'll be able to say type 1. And so the system itself gives us the ability to talk about these things.
Okay.
When trying to reason about how, what kind of consistency strength are we looking at, that's where we map it to set theory, and then we can say, oh, these equate to certain kind of large cardinals, but the large cardinals themselves won't show up in the proof assistant. What'll show up in the proof assistant is, well, you can just write down type 1, and it's like, yeah, and you can write down this, and it's like, yeah, and why is it allowed to do that? Well, because we have some.
So does the implementation actually deal with universes?
It deals with universes, it doesn't deal with cardinals.
Okay.
Unless you implement cardinals.
Yeah, so for Agda, there's actually one further catch that makes it even bigger. So in things like lean, the thing that Andrej mentioned, those natural numbers are sort of external. That still kind of holds, even if you have universe polymorphism, whereas that's not true in Agda.
Right,
You can write a function from nat to level.
Right,
So you can't actually have that change based off of what A is, for instance.
exactly. So one of the things that I mentioned here is that you have omega inaccessibles in lean, you have 2 omega in Agda. That's not because they have, well, they do sort of have more kinds of universes, but one of the things that they can do is they can put a variable here and then just quantify over all of the universes and put it in another universe. And so that gives you the ability to talk about the next one after that. And then they have another hierarchy above that, which keeps going, but you can't quantify over it, and that's why it stops at 2 omega.
Well, it's even worse than that, because you could have 2 omega without the ability to map into universes. You have 2 omega because you have type omega, and the ability to map into universes. So I don't even think it's clear what it is.
I think that's a good description.
Yeah.
Well, yeah, it's not clear what it is. It's definitely a good place to. This is a common theme with a lot of these setups is that we have some idea here, and then we try to map it, and then there's some complexity, and this is part of what I'm interested in figuring out.
Yeah, there's a flag that turns off the mapping and universe behavior, by the way. So turn that one on.
I think the condition below the power set closure should be that for every I in A, B of I is in U, not that the whole sequence is in U.
You're talking about this one?
Yeah. That should, I think it should be for every.
Oh yeah. I guess this is unclearly written. Yeah, I should have said that B is I is in U. for all I. That's probably better.
Yeah, exactly. So you need that should be like the replacement axiom, right?
Yes.
Yes.
Yeah, so you have a family of things. I don't want to say that the family is in it. I want to say that each individual element of the family is in it, and that's what gives me the extra power.
So the way that you're describing it is sometimes we need bigger sizes because of interaction between features. So for example, if we have universes and induction recursion, then these interact in a way to be a very big requirement. This kind of doesn't make sense to me because I think of features in type theory as being modular. So I think if we have a model, we can ask, are there universes? That's one universal property. Are there induction recursion? That's another universal property. How is it that you can get interaction? Because each universal property is either satisfied or not.
You don't get an interaction between these features and the hierarchy itself. These features are telling you what a universe looks like, because you're claiming it's closed under these features. So the more closure you put on your type universes, the larger they can look. This is an explicit interaction. You're explicitly saying, my universe is closed under induction recursion. Yeah, of course then it's going to be different. Right?
When you interpret them.
Yeah,
It's not about how many levels there are, it's going to be what does one of these levels look like.
So it's more like if you've proven that you have induction recursion, then it's necessarily going to be a lot harder to prove that you have universes.
They will be larger, so harder to come about, yes.
Yeah, so this interacts explicitly here with these two parts. Like the omega comes from the number of types that I have written down. The inaccessible comes from what kind of types are they? Like how many, does it allow the product? Does it allow the sigma? Does it allow inductive? Does it allow induction recursion? If the more things you add, if you add induction recursion, you get Mala. If you remove it, then you get inaccessible. If you remove dependent types entirely, then you just get limit ordinals. Okay, so now I want to tell you why you shouldn't care. So this is all well and good, but actually in practice we basically don't have to worry about this. And the idea is that the proof assistant can track these levels, right? It can, you apply these things, it will work out something, and you don't need to see what it is most of the time. The idea behind tracking them in the first place is that at least we can tell you when you decide to write down type colon type, and we want to tell you that actually that's not okay, but most of the time it just doesn't show up. And so I'll show you some examples of code here in Lean. Alright, so here I have given a basic example of defining a vector type called list, list is defined with a nil and a cons, and I have a type parameter.
What is a type star?
What's type star? Good question. So type star is a type in any universe. That is to say, it's inferred as a new kind of, like, we say, okay, there's some level, I don't really care what it is, but give me the type at that level. And so this is sometimes called the typical ambiguity. The idea is, I'm not really being specific about what level I'm actually talking about. I just say, like, I don't know, some kind of type. And then Lean sort of works it out, right? Lean works out it's not that I'm extending the theory. I'm not adding it. There's no thing here that says type star. Instead, I'm just saying that it is a kind of type. So I can write this down, and I don't have to mention any universe levels. I can write down list append, and I say, alpha, oh, wait, hold on, what type is this thing? It's actually inferred, it's type U1. So it's just sort of stuck in a type for this. I can put in, like, type star here if I want to, and that will also work. But now I can look at the actual types of these things and understand, like, okay, what's really going on here? And you can see that list is, it says, well, okay, hold on, what's this? So we actually have what's like a parameter on the declaration of list itself. So it's more like list is a whole family of declarations for each type universe. So U is sort of indexing the 0, 1, 2, and so on. And it's saying that this takes us from type U to type U. And we never had to write down a type, or a universe level. And similarly with append, you'll notice that append also got this U1 attached to it. Even though I didn't have to write, like, I could have written, append U at type U like this, and then it would also work, and these are the same thing. And so I could also write like type like this, and now I'm saying this is actually just going to be defined at the first universe, and then the other ones, it wouldn't be correct. But the advantage of defining a thing like this, where it's universe polymorphic, so these declarations are actually generic over this universe level, is that now I can write lists in, I can write lists of natural numbers, like 12 and 34. I can write lists of propositions, like 2 + 2 = 4, and Fermat's last theorem. Or I can write lists of types, like Nana and Boole. Or I can write lists.
Sorry, that's in prop. It's not one of the type levels, is it?
Yes, so I haven't mentioned prop. I probably should. So prop is a type universe. And this sort of gets into like fancy special type universes that proof assistants can also support. So in Lean, there's this hierarchy of types, and actually there's one extra one at the bottom called prop. And so the actual indexing starts where prop is 0, and then there's like, this is sort of sort 1 or type 0. So they have 2 names for the different types. I think the details of this aren't that important, but prop has additional behaviors which make it relevant for the proof assistant. But in any case, this for all is also the same. So one of the advantages of defining prop as a universe is that we can reuse this operation, this pi, as also the for all. So this for all is actually a pi type, and in fact I use that in this other example here. So this is a list of propositions, this is a list of types, and this is a list of type 1s. So the universe type, or type 0, that's a type 1. Type arrow nat is also a type 1. Also, this dependent, so that I wrote for all, but this is the same as this dependent pi. It's saying you have a pi type that for any element of type returns to you a alpha cross alpha. And this is also in type 1, and so we can write down this list of type 1. And this is made possible because list is polymorphic over the universe, right? So you can have lists at any such level. So I say that most of the time you won't have to care. You won't have to worry that like list is polymorphic because it'll just sort of automatically do this, and you never have to. You'll notice the utter lack of like universe levels that are being written here. You don't have to annotate each one to say, oh, this is at universe 0. Lean can just figure that out. There are some cases where Lean won't be able to figure it out, and luckily, and sort of on purpose, I think, this works out to be exactly those places where mathematically something interesting is going on with universes. So an example of this is cardinal. You can see that cardinal has this U here, and it is in type U plus 1. So this is actually the type of all cardinal numbers, but it's the cardinal numbers within a certain universe. And so there's bigger and bigger versions of the cardinal numbers at higher universes. Similarly, category actually has 2 universe levels. It has the objects, which are at 1 universe level, and the morphisms, which are stored inside this category object, which are at another universe level. And so this allows you to represent the equivalent of what would be locally small categories and regular categories, I guess, small categories, based on whether V is U or V is U plus 1, something along those lines. And you can see that it lives in the maximum universe. Okay. And then here's an example of, like, you can write down if alpha is in type U, beta is in type V, this thing is in type max of UV. So it's actually doing sort of algebra with these universe levels, but only a very simple kind of algebra, which is basically max and plus 1.
So that's totally outside the language of Lean, like this max of UV.
No.
Oh.
So Lean has the level, the type here can take a argument which is a level. It is not an expression. You can't put in a natural, like a variable whose type is nat, but you can put an expression which is a level expression, and that can make reference to level variables. In this case, I use this universe declaration to declare some level variables, just like I used variable to declare types of those universes. Usually you won't need to declare these universe levels, and you can just use this type star, and it gives you basically the same behavior, except the level names are unnamed.
So what is known about the type level that it has an operation called +1, it has an operation called max, and that's about it.
Yes, so it has variables, it has 0, it has +1, and it has max. It also has Imax, which is for imperactivity, and I'm not going to explain what that is.
It's a sort of.
That relates to prof being magic and special.
Is there, first, is the type star part of the syntax, or when the elaborator goes?
It's an elaborator feature. So
Okay.
it's
So
basically,
the core doesn't talk about.
the core does not know what type star is.
But
Type
it does
star
know
is
what
something that
universe
expands.
variables are.
It does know the universe, right?
Second question, are these like level expressions, etc., what they call algebraic universes?
Yes. So when you see like type max U1, U2, the fact that you can do like max whatever, you can add plus and then max and plus commute and so on. There's some little algebra that Lean has to do, and so that's they call this algebraic universes. There's another variety of this where you just have only variables can go there, and then instead of having things build up, instead you add constraints. So you say, oh, but I just have a variable here, a variable there, but I also know that this one is less than that one, or this one is strictly less than that one. And something like that is implemented in Coq.
So you have to be careful about choosing the operations, right? I guess that when designing the type theory, if you wanted to be really nasty to implementers, you could assign levels using, for example, plus instead of max, and use certain sorts of features so that you can encode Diophantine equations, and then it becomes undecidable, right?
Right, so the rules here are essentially defined by, we take all the things we actually care about, and then we see what are the minimum things we can put here, and then what's the minimum we can possibly put in level in order to make that work, right? And so that's why it has +1 and max, is because that's why we need max, and that's why we need +1. So it's a very minimalistic axiomatic thing for essentially natural number. Did you want to say something about that? Okay, so that's all. Oh.
Have you considered other things like bounded quantification? For instance, if you want to write the free monad as an inductive type, for it to end up as at a fixed level, you need to be able to say, I cannot decide.
So in Lean, this is usually accomplished by using the top level and then embedding all of the smaller types that you care about into that top level. And there's another design decision here regarding whether, like, if you have an element of this type, is it also considered to be an element of this type, or is there some embedding function that takes you from this one to that one? And different proof assistants make different decisions regarding this. Lean says that no, these are all completely separate. That thing has one type, and then there's a function that maps you to the higher ones, and that's what's used.
Is that function defined or part of the logic?
It's defined. It's U-lift, and it follows sort of from some rules of inductives.
Do you have to write it down when you
Yes, and this is a disadvantage of this approach compared to what's called cumulative universes, where if you have a thing in a lower type, it's just automatically also in a higher type.
So you mentioned earlier that you don't need to care about universes in terms of, it doesn't actually matter how many you have, but there are some weird things that can happen. Like the more universes you have, you actually get more solutions to polynomial equations. Because you can sort of girdle code statements and then essentially reflect the consistency of some theory. Like, oh, this polynomial has solutions only if z of c is consistent. So adding more universes actually creates more solutions.
Yeah, I mean, this is a variation on, like, this has more consistency strength, right?
Yeah.
The more consistency strength, the more theories you can prove consistent.
Yeah, but this does reflect in statements about just like natural numbers.
Oh yeah, and yeah, it's a statement about
But
natural.
then you're looking for
But, I
trouble.
mean, in that case, you're a logician, so you deserve what you get.
Yes.
So for the working mathematician, are these universes just a bit of administrative overhead, or are they a hassle?
They are, so I would say that it is surprising how much you don't have to see them in practice. Like, even based on what I've shown you with like the max and so on, like you'd think that, yeah, you still have to deal with max and stuff, but actually it's surprisingly little. That, you know, you can just write things down and not think about the universes, and then Lean sort of takes care of it in the background. So,
So in Kok, I remember people fighting these universes, but in Lean that's less, or?
my impression is that it's not so much. It might be that, you know, because I'm not doing category theory and things.
I don't know what that was
Yeah.
about, but I remember
Yeah.
complaints about this.
So Kok also has typical ambiguity. So you don't write out universe levels, which makes it really, really easy to get into situations where you do something messed up like 5 hours ago, and you should have noticed that it was messed up when you went to go write the type, but it just inferred it. So you do a bunch of work, and then you hit a problem super late.
Yeah,
So-
this is a downside of when you try to build a system which completely hides it from you,
Yeah.
but also is not, but is still trying to give you error messages regarding it. Then you might end up in a situation where you wrote something wrong and it didn't tell you about it because it's like, I can find a way to interpret what you said, and then a long time later. It's like, oh, you have a universe inconsistency. And it's like, what's a universe? And how do I fix it? So that can also be.
I think all other questions, of which there seem to be none now, can be handled during the cake break, or if you're lucky, during the lunch break. So I'll make the same announcement I do every day. We'll meet back here at 2 o'clock, and who knows what comes then.